Hey guys, welcome back to chapter 14. So what we're going to do today is continue our discussion of the rate law, and we're going to quantify this. So we already said that the rate law has to be determined experimentally. So what would that look like? What's the data going to look like, and how do we crunch those numbers to determine if it's first order, second order, third order? Okay. So just a quick review. Here's our three orders. And one of the things that we discussed is that a zero order is independent of concentration. So it doesn't matter how much we have. This is going to proceed at the same speed or rate. First order depends on it, and it depends on it in a directly proportional relationship. So first order reaction is directly proportional to the concentration, rate and concentration. And second order is proportional to the square of the concentration. So this is going to slow down much faster. Okay. So how do you determine the order of a reaction? Well, it has to be done experimentally. You have to look at numbers. So I cannot on a test or a quiz give you a reaction and say, what's the reaction order? You've got to see the data. You got to see the numbers. Okay, so let's look at this first one. So here's how we would gather this data. So we've got to have some way to measure the concentration, okay? So a concentration of our reactant, and then we're going to somehow be able to measure the rate. So when the concentration is 0.1, what was the rate of that reaction? How fast did it happen? When the concentration initially was 0.2, what was the rate, or how fast was that reaction? When the initial concentration was 0.4, how fast was that reaction? Okay, so we're going to start with different amounts of our reactants, and we're going to measure the rate of that reaction. Certainly, rate is going to have something to do with time, so there'll be a timer involved. And we'll see exactly how we get to rate when we start to do this lab in a couple weeks. Okay, so start with different amounts of the reactant, measure the rate, and then we're going to compare two of the trials. So we may compare trial 1 to trial 2. We may compare trial 1 to trial 3. For this one, it doesn't really matter which one we compare. We'll just look at two of the different trials and see how the rate changed based on how much we have. Okay? So probably the first thing you guys are going to do is trial 1 and trial 2. So what do you guys notice about the concentration of A between trial 1 and trial 2? So the concentration of A between trial 1 and trial 2 doubles, right? So we multiply it by a factor of 2. So here, it doubles. Okay. And what happens to the rate of this reaction? So the rate was 0.015, double the reactant. What happened to the rate? It also doubled, right? So if we double the concentration and we see that the rate also doubles, we would say that those two are directly proportional. Or what kind of order would this be? Yeah, it's a first order reaction. Double concentration, double the rate. Double concentration, double the rate. Okay. If you are not just seeing this, right, jump off the paper at you, that is okay. I have a formula that we can use in order to crunch these numbers and get it that, n equals 1, without just seeing it on the paper. So if you're having a hard time seeing double, that's okay. There's another way to figure it out. Okay. What about this reaction? So again, we did 3 trials. Okay, and each trial, we increase the amount of the initial reactant. So we doubled. What do you notice about the rate? So trial 1 to trial 2, I doubled the concentration of the reactant. What happened to the rate? Nothing. And then I doubled the concentration again, and what happened to the rate? Nothing. So this one appears as though it doesn't matter how much reactant I start with, the rate is always going to be the same. The rate is always going to be independent of the amount. So this would be a zero order reaction. Okay. So it doesn't matter how much we started with, the rate was the same. Sublimation. Okay. What about this one? Same setup here. So trial 1, trial 2, trial 3. Double the concentration for each trial. Monitor the rate. Okay. What happens to the rate? This one's a little bit harder to see. But when I doubled the rate between trial 1 and trial 2, that quadrupled the rate. Double the concentration, quadruple the rate. 15 times 4 is 60. And then trial 2 and trial 3, I doubled the concentration again. And again, the rate is quadrupled. Okay? 60 times 4 is 240. So if it is proportional to a square, this is a second order reaction. Second order reaction. Now, this one I understand is not as easy to see. The zero order, of course, that's easy. It stays the same. That's zero order. First order, you can kind of squint your eyes and figure it out. 15 times 2 is 30. 30 times 2 is 60. So that one you can kind of squint your eyes and figure out. This quadrupled one isn't as easy, right? And what if the numbers aren't nice and pretty and clean like these are? They're not going to be in the lab, right? They're going to be messy numbers. So let's take a look at how we can determine this mathematically. What if you're unsure of how it's changing? So here's the formula that we have. We can look at the concentration and the rate of two different trials. So it doesn't matter which trials that we pick. All that matters is we stay consistent. So if trial 2's on the top, trial 2's on the top. And if trial 1's on the bottom, trial 1's on the bottom. Okay? If you happen to pick trial 3, so trial 3, they both need to stay horizontal to one another. Okay? And the variable that we're actually solving for is this guy right here, the y. So y is going to tell us the order of the reaction. Okay? So once we solve for y, it's going to be a 0 or 1 or a 2, and that'll tell us what the order of the reaction is. Okay, so let's look at an example here. We know this one was second order, but let's prove that to ourselves. So let's do trial 1 and trial 2, trial 1 and trial 2. It doesn't matter what number you put on the top, what number you put on the bottom. This is all going to come out the same. I like to always put the bigger number on top because then I'm dealing with whole numbers instead of fractions. But if you happen to switch them and put the smaller number on top, it's still going to work out. Okay, so I'm going to put trial 2 on top. So the concentration of trial 2 is 0.2 molar. And the concentration of trial 1 is 0.1 molar. And it's raised to the power y. That's what I'm going to be solving for. And then I'm going to do the same thing over here. So the rate for trial 2 is going to go on the top, 0.060. And the rate for trial 1 is going to go on the bottom, 0.015. Okay. So from here, you can clean this up a little bit. I can take 0.2 divided by 0.1. And I'll see that that is 2 raised to the y. And you can take 60 divided, or 0.060 divided by 0.015, and you'll see that that equals 4. Okay. So here's another kind of shortcut cheat sheet way out. Okay. So you can look at this and say, oh, well, I know that 2 squared equals 4. So y must equal 2, right? 2 raised to the second power is 4. I know that y must be 2 here. That would work, okay? So if you didn't see it originally, but now that becomes crystal clear when we get to this step, then you can stop there and say, hey, Miss Mazz, this is a second order reaction. If these numbers, again, are not this pretty, or you're just not seeing it at this point, we can solve for this y. So how the heck do we solve for an exponent? How do we get that exponent out from up there and in a usable format where we can do some algebra and solve for it? So this is going to take you way back, but to get that y down, we're going to take the log of both sides. Okay. And what taking the log of both sides does is it takes this y and it throws it in the front. So the log of anything raised to an exponent is going to be, the exponent log times the base. And whatever we do to the left side, we have to do to the right side. So again, there's kind of an imaginary exponent of a 1 there. So you can picture that 1 coming down. But all you have to do on this side is just log of 4. Okay. Well, Miss Mazz, how does that help me? There's logs now, and that's crazy. Well, type that into your calculator. Okay. So use your super smart calculator and let it do all the hard work for you. So if I literally type into my calculator log of 2, that's going to equal, so y, that's going to equal 0.301. And if I literally type into my calculator log of 4, that's going to be equal to 0.602. Okay? Let me clean this up a little bit just so you can see it. So now I don't have logs anymore. Now I have actual numbers, and I have a variable that's not an exponent anymore. So how do I get this y by itself? I divide by 0.301, divide by 0.301. So again, type that into your calculator if you're not seeing it. So 0.602 divided by 0.301, and we get that y equals 2. Okay. So no matter which way we slice and dice this, this is a second order reaction, okay? So when we double the concentration, the rate gets quadrupled. Well, not all reactions are A becomes the product, right? There's a little bit more to it than just one reactant, one product. So when we have more than one reactant, our rate law is going to get a little bit more complicated. So if we've got reactant A reacts with reactant B, and again, we're just forming product, we don't care what it is, this is what our rate law is going to look like. So rates equals, we've still got that K. We're going to take the concentration of A raised to whatever power it is, times the concentration of B raised to whatever power it is. So when we crunch the data here, we're going to have to determine the order of A. Then we're going to have to determine the order of B. So it may be a second order and a first order. It may be a first order and a zero order. It may be a zero order and a zero order. So we've got to determine that experimentally. So we're going to have to determine the rate of each of the reactants and then put that number into the formula here. Okay. We'll talk about this in just a moment, but the overall reaction order, so for this entire reaction, would be just simply adding M and N together. So for example, if this was a first order and a second order, the overall reaction order would be a third order. Okay, so we just simply add those two together. Okay. So let's take a look at just a quick example. If A is a first order reaction and B is a second order reaction and C is a third order, what is the overall reaction order for this reaction? Yeah, so it's just 1 plus 2 plus 0. So this is a third order reaction, overall reaction. Okay, third order. All right. So let's look at an example, a real life example with real data to see if we can determine what is the reaction order for each of these reactants. Okay, so here's the chemical equation that we're going to be looking at. So NO2 reacts with carbon monoxide to produce these products over here. I don't care what their products are. So ultimately, what I want you guys to do, what we're going to be able to do at the end of this, ultimately, I want to be able to write the rate law, okay? So write the rate law. So we're going to have something like rate equals K times the concentration of one of our reactants times the concentration of our other reactants, and we need to be able to fill in these numbers here, right? So this is going to be the ultimate goal. This is what we're trying to reach to, is get that rate law written on our paper. Okay, so let's look at the data to get there. So here's our data. We did 4 trials of this experiment, okay? So in trial 1, we used this same amount of concentration, so 0.1 and 0.2. Trial 2, we changed one of them. Trial 3, we changed both of them. Trial 4, we changed both of them. So what we need to do is we need to isolate trials that will give us the reaction order. What I mean by isolate trials, if I want to know what is the reaction order for NO2, I need to look at 2 trials where NO2 changes, but I can only change one variable at a time. So I look at 2 trials where NO2 changes, but CO has to be the same. So I could not look at trial 1 and trial 3, because even though NO2 changes, CO does not, or also changes. So I can't have 2 things changing and still get a clear picture. So to determine the order of NO2, I'm going to look at trial 1 and trial 2. Okay. These change, these stay the same. Let's look at the rate. Okay. So for NO2, we're going to be looking at the concentration of trial 2, so 0.2 over the concentration of trial 1, which is 0.1, raised to that y. Okay. And then we're going to look at the rate. So the rate for trial 2, which is 0.0, oops, missed a 0, divided by the rate at trial 1. And we're going to try to determine what is y, what is the value for y. So the first thing I'm going to do is just kind of clean this up a little bit. So I'm going to take the 0.2 divided by 0.1. So this is going to be 2 raised to the y. And then I'm going to do the other side, 0.0082 divided by 0.0021. And this side is going to be 3.9. But again, let's go ahead and round to whole numbers. It's going to give us a clear picture. So if I round this 3.9 to 4, what order is NO2? 2 squared is 4, so y must equal 2. Okay. So NO2 is second order. Now what I want you guys to do is I'm going to pause for a minute. I want you guys to determine which trials would be good trials to determine the order for CO2? So which two trials do you think we're going to use? Okay. So we need two trials where CO changes, but NO2 stays the same. Well, these are the only trials where NO2 stays the same, so hopefully CO changes, and it does. So we're going to use trial 2 and trial 3. So stays the same, changes, there's our rates. Ooh, look at those rates. This is the easiest one. When I double the rate of CO, does the rate of this reaction change? Nope, those are basically the same number. So right away, we can see pretty quickly that CO is a zero order reaction. Okay. So that's how we use the data to give us the orders when we have more than one reactant. We've got to look at the trials and make sure we're changing one thing at a time. Okay. So let's write the rate law. So write the rate law for this reaction. Okay. So the rate law, rate equals, it's always going to have that constant K in there. So rate equals K, that's a cursive K if you're wondering. Rate equals K times the concentration of NO2. And now that we know that it's a second order reaction, we can put that exponent 2 up there. Times the concentration of CO. And now that we know that carbon monoxide is a zero order reaction, we can put that 0 up there. So that is the rate law for this reaction. I got way ahead of myself here, so I'm going to just kind of click through because it asks for all these things, and I already did it on that slide. A complete rate law for this reaction, we wrote that. Okay. The other thing that I'm going to ask you guys to do is to solve for this rate constant K. So let's get our rate law written down here. So rate equals K times NO2 squared times CO 0. Okay. So if I ask you, what is the rate constant K for this reaction? What I'm asking you to do is pick a trial and solve for K. So if you pick a trial, you know concentration, you know the rate. The only thing that we don't know is K. So we just got to do some algebra to solve for that. Okay. You could pick whatever trial you wanted to pick. It doesn't really matter what you pick. Likely, most of you guys are going to go ahead and pick experiment 1, I would imagine. So let's go ahead and pick that one. So we're going to plug the information from trial 1 into our rate law formula. So what is rate? Well, in trial 1, the rate was 0.0021 molarity over seconds. Okay. And that equals K. That's what we're solving for. In trial 1, what was the initial concentration of NO2? Well, it was 0.1 molar. And that's a second order. And then the initial concentration for carbon monoxide was 0.1 molar. And that's a 0 order. Okay. So now we see that we have all of the numbers except for K. Now we just need to plug and chug and solve for K. The hardest part about these problems really is the units. Okay, so we're going to have to be very mindful of our units as we go through this problem. Okay. All right. So Nothing really to do over here on the left side, or right, yeah, left side. So I'm just going to rewrite this as 0.21 molarity over seconds. We've got K. All right, so now we need to square this. So 0.1 squared equals 0.01. And if I square the number, that's also going to square my unit. So now that's molarity squared. Okay. And then this guy is raised to the 0 power. So anything raised to the 0 power is just 1. Okay. All right. So now we just need to do some algebra to solve for K. So I'm going to divide by this side. So I'm going to divide by 0.01 times 1. Whatever I do to the left side, I also have to do to the right side. Okay. So the number is pretty easy. So just plug 0.0021 divided by 0.01, and that equals 0.21. And that's easy. Okay. What's a little bit more difficult is our units here. Okay. So looking at our units, I've got molarity on top, seconds on the bottom, and then I got this molarity squared also on the bottom, okay? So the seconds stays the same. There's nothing to cancel that out. So that seconds is still on the bottom of the fraction. But what about these molarities? So I've got molarity on the top, molarity squared on the bottom, so one of those goes away. So I've still got this molarity on the bottom. So what are the units for K? Yeah, they're kind of funky, right? Remember, this is our bridge between concentration and rate. So the units are going to be a little bit weird. They are going to be kind of a funny bridge. So the units for K for this guy is 1 over molarity times seconds. Or often you'll see it written like this. Okay. So K equals 0.21 molarity to the -1 seconds to the -1. Okay. So that was a lot I just threw at you. I'm going to do another video where I work through 1 or 2 more examples of the exact same thing. So I'll go through another video. But what I want to end this video with is these units for K. So if you follow your units through this problem, they're pretty easy to determine the units for K. But in the event that you want something to kind of look at to check your answer, to make sure you're right, here's the units. So these are going to be for overall 0 order reactions, overall first order, overall second order, and overall third order. So our overall reaction here was an overall second order reaction, right? 2 plus 0 is a second order reaction. So if I look at our units for K, they should have been molarity to the -1, seconds to the -1. And when I followed that through my problem, that's exactly what I got. So these should always match up, okay? If it was a first order reaction, it would just be seconds to the -1. All the molarities would cancel out, so on and so forth. So this is just a really good slide to have access to. I'll put it in the helpful handouts. It'll help you with the units for K, and it's just a really nice way to check your work. Hope you guys found this helpful.